All right, now we're into the second section of this first inquiry point. Now, one thing that if you haven't realised so far, when we've been looking at the syllabus dot points, it's quite intricate and there's a lot of stuff packed into each syllabus dot point. So that's why there's lots of videos here. We're going to be unpacking the syllabus point and there's a lot of crossover. So this is why students usually find this particular module quite challenging, because the way they construct their syllabus dot points, a lot of information can come from it. So that's why I'm making a separate section now here in terms of magnetic fields, because the whole inquiry question for the first section is about particles and electric fields, and now we're doing particles and magnetic fields. So let's delve into this and let's pull this apart and get a better understanding. Okay, so as you can see here, it says we're going to analyze the interaction between charged particles and uniform magnetic fields. And so we're going to revise a little bit of magnetic fields here from what we did in year 11, and then we're going to start adding some new points to that. Okay, now it says when we look at these charged particles, we've got to look at it in terms of acceleration, perpendicular to the field, etc., etc. So this stuff here is in the next series of videos coming up. This first video in this section is just really going over what we remember from year 11 in terms of what a magnetic field is, the different types of magnetic fields, etc. All right. So let's get into this one. So remember from year 11 we said that magnetic fields are a region in which a magnetic object experiences a force. Okay, and we're going to have our pretend magnetic object here as a north pole. Remember that poles cannot be monopolar. You can't have a singular pole there. It has to be dipole, a north pole and a south pole. But just for in purposes of being theory here, we're going to have a test north pole. Okay, if you remember when we did electric fields, we defined the electric field as the direction in which the field would go when a test positive charge would move, right? And so that helped us understand which direction the field was going in. Well, here by definition is the direction of the magnetic field is the direction in which a north pole would move. Okay, and so we can see here we've got some bar magnets, and so if I was to just enlarge this diagram for you, okay, if we've got a north pole here and I have a pretend north pole, so let's at least do it in a similar color red. So if I have a little north pole here, then like poles repel, and so this would move in that direction, and so therefore the direction of the field is moving away from the north pole towards the south pole, and so we place arrows on these field lines. Remember that these field lines are just a graphical representation of where the field would go, and of course we can use iron filings to what we do in junior school to show the location of these fields. But there's some important points about these fields we must remember. The first thing is their direction is always from north to south. Okay. The second thing is they don't cross. These field lines do not cross over, and the density of the field lines affects the field strength. So you can see here that the distance between this field line and this field line is further apart, whereas down here they're closer together, and so therefore there's a higher density of field lines per unit area, and that's going to give us a stronger field there. Okay, the force, the magnetic force, is going to be stronger, and we're going to get into that concept about flux density, etc. in later videos. But just keep in mind now we're just going to keep it simple and say if they're further apart, then it's a weaker field. If they're closer together, it's a stronger field. Okay, so there's our diagram, and we know that when we have poles like this and opposite north and south, that they attract each other, okay, like so, and then if we have like poles, they repel each other, and they're classic experiments that you do way back in year 7. Okay, if we now have a look at a diagram here, we can see this general structure around a bar magnet. So we can see that we've got these lines going like that. We can see that they're sort of coming out and going around. So this is observed in these iron filings aligning themselves with the field to create this pattern. Okay, and so we've seen that. So remember that if we have a test particle here, that there is going to be a force experienced by that particle within that field line. And remember, force is a vector, and so we're going to have a direction in which that force is going to go and a magnitude. We've already talked about that the closer the field lines, the greater the magnitude, of course, and then the direction would be the direction in which the field is moving. So there is a different magnetic force on at that particle. Back in year 11, we also explored fields in terms of different ways. We just didn't look at a bar magnet, we looked at fields around horseshoe magnets, but then we also looked at this connection between electricity and magnetism, and we're going to get into that in more detail in this unit. Right, this weird connection between electricity and magnetism, and we're going to be looking at some classic experiments that were done to show this connection. But we looked at the understanding that if we have a wire and if we pass a current through that wire, then there was a magnetic field that was induced or created. Okay, so a very important term, induced, means to create, and we're going to be coming back to that term later. But here we have a positive going up like this towards the negative. Now, here is an interesting point which you've got to remember. These diagrams are written according to conventional current. Now, conventional current is the direction in which the current goes, a positive current goes. And so we have directional current, and so that's why we can see we've got a positive here, and we've got the arrow going up. That's the direction of conventional current coming from the positive into the negative. But of course, as we found out more information about the structure of metals and the movement of ions and electrons, we now know that this electricity current is due to electron flow. So even though the positive current is going that way, electron flow is going in the opposite direction. Okay, and that makes sense, because if we were to draw like a little electron here, there it is, whee, then it is being repulsed by the negative ion there because it's negative, and it's been attracted to the positive ion. So electron flow would be going in this direction. But remember, when we do a lot of our rules, some of the rules you learnt in year 11 and more rules today, like this right-hand grip rule, when we're talking about current, we're talking about conventional current. So your thumb will be pointing in the direction of the conventional current. And so this is where I want you to get your hand out now, your right hand. And we're going to determine the direction of the field around a current carrying conductor. Now notice the terminology I'm using there, right? So highlight this terminology, current carrying conductor. Okay, so I'm using the subject-specific terminology of the syllabus, and you're going to come across this in HSC questions as well. And it's just a way to describe something, but a current carrying conductor is the sophisticated way of saying a wire, right? It could be a bar, right? A metal bar is the current carrying conductor. So we're going to do the right-hand grip rule around this current carrying conductor, aka a wire, and determine the field around that wire. So let's get your right hand out, and what you're going to do is you put your thumb in the direction of conventional currents, that's up, there you go. Then your fingers will curl in the direction of the field. Okay, and so here you can see my picture here. I've got the thumb going up, positive, for the positive conventional current. My fingers are going around according to the direction of the field, and you can see that that is showing you this example right there. The field is going, and we might even write this down, the field is going in an anti-clockwise direction. Okay, so we can use the right-hand grip rule to find out the direction of the current in a wire, and so this wire going up like that, okay, the current's coming towards you. So we're going to be learning and revising, you probably remember from year 11, if I was to look at this wire from above, then how do I draw that? Well, I draw that as a dot. That dot represents that the current is going up towards you, and we're going to talk about that later on, but it's sort of trying to give you the analogy of an arrow, right? An arrow is like a direction. So there's the tip of the arrow. This is the tip of the arrow coming towards you. And here, where the current's going in the opposite direction, the current's going down, and it's like the arrow is moving away from your face. If the arrow is moving away from your face, then what would you see? If you were to look at that end of the arrow, you'd see like a crosshair like that, because they're like the feathers of the arrow moving away from you. And so therefore, if we were looking at this wire from the downward perspective, we would see a cross. Okay, so a cross represents current going away from you, and a dot represents current coming towards you when we're talking about current carrying conductors, right? We're going to use similar dots and arrows when we talk about magnetic fields, but that's in a later video. It might even be this video, I can't remember, but anyway, we'll keep going. So if we use our right hand grip rule now to prove that this diagram is correct, so get your thumb, the current's going down, so we're going to put our thumb going down, and then our fingers are going to curl in the direction of the magnetic field, and you should find that it's in the same direction as this diagram just there. And so the current is now going in a clockwise direction. Okay, so we have magnetic fields that are induced, that is, that created when you turn on electricity, and we're going to do that experiment later on in this module. We also had this scenario here where we made up a coil of wire in year 11, which was called a solenoid, and that solenoid created a magnetic field, like a bar magnet, right? Remember we said previously in the last slide that a bar magnet has the north pole here, right, because it's got the arrows coming out of it, so that's a north pole, and the south pole there. Okay, and if we use our right hand grip rule, but for solenoids, right, so we modify this right hand grip rule now because it's the right hand grip rule for solenoids, we put our thumb in the direction of the north pole, right? So if we now get our thumb and go like that, it's in the direction of the north pole, then our fingers will curl in the direction of the electron flow. So that means that in my diagram, the wire around here, it means that the, let's have a look. This diagram might even be drawn incorrectly. Let's have a look. We've got our thumb going down, so it means that the current should be going that way, right? And that means if the current is going that way, in terms of that, it means this diagram is incorrect. So the person who did this diagram wasn't really a scientist or a physicist. They just thought, oh yeah, that looks cool. So direction of electric current in wire, so it really should go the other way in terms of our electron flow. Or what we can do is we can flip this field around, so instead of the south being at the top, we would make that a north. So just keep that in mind, that diagram is not 100% correct, but the right hand grip rule is what you use to determine the direction of the current in a wire, and your thumb goes in the direction of the north pole. So that's it for a quick revision of magnetic fields. We had a look at magnetic fields when, or static magnetic fields that were produced when current was flowing. Okay, we saw that to begin with what a field was around a bar magnet and the direction of the field. We saw that we can use the interaction of North Pole, South Pole, etc. to come up with some diagrams. We then talked about these wires and current carrying conductors and how we can use the right hand grip rule to determine the direction of that field, and then we did the right hand grip rule for solenoids. So that is a quick revision of year 11. In the next video we're going to be looking at what happens if a charge is moving by itself, because if you remember in terms of our syllabus dot point, it says that we have the interaction between charged particles and a uniform magnetic field. Okay, so when the field is stationary but a particle is moving within it, what happens? Okay, and I'll see you in that. Right, before we go to the next video, I want you to check out
more courses that we have here on our YouTube channel, which are just small snippets from the actual bigger courses that we have on theflipteacher.com. Of course, with all of our courses, we try to incorporate practical sessions. We have study cards, we have posters that you can print off and stick around your room and do a lot more. We have up to 68 or more videos per course. That's like 9 to 10 hours of material that really delve deep into the syllabus and looking at essential content, skills, mathematical manipulations, and a lot more. So if you like that, go over to theflipteacher.com and check it all out, and I'll see you in the videos.